calculus word problems. We're going to take derivatives with respect to time of functions to see how things are moving at a specific moment in time. It's no longer going to be tangent slopes, but it's like how quickly is something changing. It's no longer dy dx. We'll find maybe dy dt or dx dt or dv dt. We're going to be taking derivatives with respect to t. It will help us find the instantaneous change of whatever we're finding the derivative of with respect to time. So how quickly is something changing at a specific moment in time? Okay? We're used to taking derivatives with respect to x, so we should be comfortable with these. If you see d dx of y, you know that's dy dx. Tangent slope, instantaneous change of y over instantaneous change in x. Tangent slope. Take the derivative of y cubed, 3y squared, dy dx. Take the derivative of x with respect to x, you get 1. It could also be viewed as dx dx. Well, what if we took the derivative of those four things, those three things plus 1, with respect to t? Okay? How would my derivatives change? Well, instead of having dy dx, my derivative would be dy dt. That's how much are my y coordinates changing at a specific moment in time. Am I going up or down, and how quickly? Y cubed. We would apply the chain rule similar to what we did up here, implicit differentiation, only it would just be 3y squared dy dt instead of dy dx. The derivative of x no longer is 1. It's 1 up here because the variables ended up canceling each other out. It's the instantaneous change in x with respect to the instantaneous change in x. Well, it's just 1 here. This ends up being dx dt. But now, if we find the instantaneous rate of change of time with respect to time, this becomes 1. This is dt over dt. The variables agree with each other. Okay? We can have certain equations, x's and y's, expressions, and we can find the derivative with respect to t of those. These are basic ones. We will be taking formulas that we know from geometry, from other classes, from other math classes. We will be taking derivatives of those formulas with respect to time. Now, we will always have something after our derivative, and we have to be sure we have the correct form. This is dx dt, this is dy dt. Over here, you have to use the product rule. Nothing goes away, nothing turns into 1. We need every single derivative with respect to t and every variable. Okay? And again, this was just the derivative of x times y. This is derivative of x times y plus derivative of y times x. This is the product rule. All right. Well, we call these problems where we're taking derivatives with respect to time related rates problems. Okay? And here's a simple related rates problem. I'm giving you an equation, x plus y cubed equals 8, and I'm asking you to find dy dt, but I'm giving you some information. I said find dy dt when y is equal to -2 given dx dt is equal to 2. Now you know you need to find dy dt. It means you need an equation with dy dt somewhere. The only way you can get an equation with dy dt in it is if you take the derivative of this with respect to t. Okay, so I will take the derivative with respect to t of my entire equation, and let's see what I get. I get dx dt plus 3y squared dy dt is equal to 0. Right? Now, if I asked you to just find dy dt, you could solve this for dy dt. But no need. We can just get some information that we have, plug it in here, and then solve for dy dt with some numbers rather than all these dx dt's and these y's. So I'll just plug in 2 for dx dt, which was just given to me right here. I will plug in -2 for y, which is just given to me right here. And I will be able to solve for dy dt. Okay? So for this implicit equation, if you talk about things moving at a specific moment, if dx dt is moving to the right constantly at 2, we could say that the y's are changing. They're going down 1/6 of a unit at that specific moment in time, whether it's per second or per minute or per whatever. Question, Mr. Ramanetti? Okay. Here is another one. Let's look at this. We get z squared equals x squared plus y squared. dx dt is 2. dy dt is 3. Find dz dt when x is 5 and y is 12. Oh, we can use our calculator today if we want to. We'll be able to use our calculator on our test coming up as well. It won't help us that much. We won't use it that much. But just to make sure we're not messing up on calculations, especially with these problems, we can use it. It might help you for this problem. I actually can find that z that wasn't given to us, and we can actually get just a numerical answer for dz dt. How do you think I find z for the situation, Mr. Ramanetti? Yeah, you can find what z is when x is 5 and y is 12 using my original equation. It ends up being 13 because it's a 5, 12, 13 right triangle if you think about a squared plus b squared equals c squared. So you get z squared is equal to x squared. Typically, we will stick with positive values. I know you would say it would be plus or minus 13, and it's right, but we'll kind of keep things on the positive areas for this lesson. So you end up with dz dt is equal to 46 over 13. That does not simplify. Okay, we will be using original equations a lot when we get to progressively harder related rates problems. This is like an easy one in that you don't have to kind of write anything down. The information is given to you. You just have to take the derivative correctly. The one difficult part is, hey, we can find z using the original equation when x is 5 and y is 12. Okay? All right, those are simple ones. Those are just given information. You'll have some of those for your homework. But real ones we're going to be talking about will be like this. Volume of water in a container is given by the equation that's where h is the height of the water. The water level rises at this rate. At what rate is the volume increasing when the water is at height of 3? Spherical hot air balloon is being inflated. The air balloon into balloon is at the rate of 2 cubic feet per second. How fast is the radius of balloon changing? The side length of a square is shrinking at a rate of 2 feet per second. How fast is the area of the square changing? Okay? And the way we're going to do this is we are going to take formula that we know and take derivatives of it with respect to t. Like, let's start with one that we will use. Volume of a sphere. Let's start with the volume of a sphere. Volume of a sphere is 4/3 pi r cubed. We will be taking the derivative of that with respect to t to see how my radius and my volume will be changing relative to one another. Watch what happens when I take the volume of a sphere with respect to t. I get dv over dt is equal to 4/3 pi is just a constant. It's just a number. So we're not going to worry about 4/3 pi, but we will take the derivative of r cubed. Well, it'll be 3r squared dr dt, 4/3 pi times 3r squared dr dt. And then you can cancel the 3's, and you have 4 pi r squared dr dt. So it turns out the change in my volume of a sphere is related to the change in my radius, how fast my radius is growing, and the radius's size. So another one we'll be using, area of a circle. A is equal to pi r squared. Notice that we need both sides. You're not just going to have pi r squared. You need a variable equal to pi r squared because we need that stuff on the left and on the right. Don't just put down the half of it. All right, take the derivative of an area of a circle with respect to t. You get pi 2r dr dt. I wrote it as 2 pi r dr dt. We'll be using the Pythagorean theorem a lot with these questions. This is how we're going to calculate distance between two objects. I usually go with d squared is equal to a horizontal distance squared plus a vertical distance squared. And you can take the derivative of this with respect to t. To capital D, dd dt equals 2x dx dt plus 2y dy dt. Here's one that a lot of people screw up with. Trig functions of angles. Let's say we have the cosine of theta is equal to some ratio. I'm going to give you a value for the numerator just so that we don't have to do a crazy, hold on, let's make that correct. Cosine is equal to adjacent over hypotenuse, so I'll say this is d. Sometimes you'll be given a side length. We'll talk about that in the future. But you'll need to take the derivative with respect to t of this formula. What would be the derivative of cosine of theta? Negative sine theta d theta dt. And then this can be written as 5d to the negative first. You don't have to use the quotient rule. It'll just be negative 5 over d squared dd dt. Okay, we're taking derivatives with respect to time of all of these great things, okay? And there's going to be more that we're going to do, volumes of cubes, circumferences of circle, but this is the general idea of things, okay? Yes?
Can you explain again why, like, for volume of circle, why you use the 4/3 pi?
Right, because it's not a variable, pi is just a number. So if I thought of pi as a variable, yes, you'd use the product rule, but it's not. It's just a number, so it's just a constant. Take the derivative of the r cubed, 3r squared dr dt, 3r squared dr dt. You can multiply the 3 by the 4/3. You just get 4 pi r squared dr dt. Okay? Okay, but the a and the r, variables for sure. Yeah, quick. To be able, given a word problem, to express things using this calculus notation of changing rates. Okay, so in a question, it might be stated, the radius of a circle is growing at 3 inches per second. Well, if you're using r for radius, you would say that the rate that the radius is increasing with respect to time, dr dt, equals 3. And all of a sudden, you now have calculus notation, and you will be able to use that information similar to how we use the information on our easy word problems right here. Just it won't be given to you. You'll have to be able to, write it down, extract that information from the problem. If the perimeter of a rectangle is shrinking, if they talk about things decreasing or shrinking, you need to know, and I'm using P for perimeter, that dp dt is equal to -5. Okay, something decreasing, make sure it's negative. Something shrinking, make sure it's negative. Going down, moving to the left, all negative. Okay? If we're talking about a horizontal distance, we usually use x to be a horizontal distance. I would say dx dt is equal to, it's decreasing by 2 feet per second, -2. Okay, vertical distance would be a y. Okay, let's do it. Let's start with the simpler ones. It is a word problem. However, we're given most of the information. Nothing's too complicated. We're just going to take the derivative, plug in some information, and then we'll have our answer. So stuff you need to write down is that the volume of the container is given by this. H is the height. You might need to write down that the water level rises at 2 feet per minute. The question is, what rate is the volume increasing? When the height equals 3. Now, step 1 is to make sure I have all the information extracted out of the problem, written down using calculus notation. Okay? We already have the formula, which is nice. Just write that down again. I would say V, or V of t, if my thing works. I'd say V is equal to 10h cubed 4 minus h. Water level rises. That would be the height of my water and how it's changing. This would be dHdt equals 2. See, I can kind of figure that out, throw that down on the paper. That's going to be important to use. The question is, what rate is the volume increasing? The rate at which the volume increasing would be dV dt. And we're going to try to figure that out. When the height of the water is 3. You can say h equals 3 or when h equals 3. Now, here's the key. You can't just plug in 3. Okay, because the height of the water is changing. It's a variable quantity. If there's anything that was a fixed quantity that's always going to be the true, that can change my formula, I can plug that in. But if we have things that are changing, don't change it. We're finding dV dt at the specific moment when the height is equal to 3. So this will only get plugged in after taking the derivative. And really, all of our information in this situation, we will plug in after I take my derivative. But that's all I'll have to do is take my derivative, plug in information, and I'll be able to find dV dt. Now, in this situation, we could use the product rule. However, I could distribute the 10h cubed as well. Either way would give you the correct answer. But maybe one way is a little bit easier than the other. Let's just use the product rules. Let's say we don't recognize that we can distribute. We'd get 30h squared dH dt times 4 minus h plus the derivative of 4 minus h, which would be negative 1 dH dt times 10h cubed. Okay? This would be, I think, the more difficult way to do this. I would prefer that you distributed this first. Okay, now, dV dt is over here. This is what we're trying to find. We have when h is 3. I'll plug in 3 everywhere. I'll plug in 2 for dH dt everywhere, and I'll solve. And this is where a calculator comes in handy. She moves her chairs twice a day. I'm certain of it. At least twice a day. Okay, this is a numerical answer. We can get that. That's the answer. Okay, that's how quickly that the water is changing. Probably pretty quick. Actually, this is a negative value. This is a positive value. So maybe they kind of cancel each other out a little bit. Anybody calculate that? Was it? That's incredible. What a great answer. So it turns out at the specific moment, The water's not changing at all. Fascinating. Neither increasing nor decreasing. Let's tackle the spherical hot air balloon. It's being inflated. Air is blown into the balloon at a rate of 2 cubic feet per second. How fast is the radius of the balloon changing when the radius is 3 feet? You will be given your formula for all of these situations, so you don't have to memorize those things, which is nice. But the volume of a sphere is 4/3 pi r cubed. All right, get your information, take your derivative, plug in your information, find your answer. Air is being blown into the balloon. What is that giving you? How can I write that using calculus notation? Miss Pariar, you just wrote it down? Exactly. dV dt equals 2. My question is, how fast is the radius of the balloon changing? What am I trying to find? dr dt. When the radius is 3. Don't plug in 3 here. It's just how fast is it changing at the exact moment when the radius is 3. Instead, start with your formula, take the derivative, plug in your information, and you will get your answer. I need the left side too. So 2 equals 4 pi times 9 times dr dt. I get dr dt is equal to 2 over 36 pi, or 1 over 18 pi. Okay? Now, this is a radius. This would be in units to the first power per second. This one was a volume. This would be units to the third power in whatever time that we're talking about. If we're talking about area, it'd be units to the second power for whatever amount of time. And they're not super strict on units in our class. However, it's good to keep them consistent and correct. Next one, the side lengths of a square are shrinking at a rate of 2 feet per second. How fast is the area of the square changing? When the side length equals 4 feet. I didn't give you enough information. Now you have enough information. Now, I would not give you the formula for this situation. You'd have to generate your own formula, and you'd have to take the derivative of it. You're expected to know the area of a circle, the circumference of a circle. You're expected to know area of like rectangles, triangles, squares, certain things like cones, cylinders, spheres, equations with pies. They give those to you, but they won't give you this one. You need to start with your formula that's not given to you, which is a is equal to s squared. The side lengths, ds dt, are decreasing at 2 feet per second. S is 4. We need to find dA dt at that moment. You have to first have your formula. You need to get dA dt, so you take the derivative of that formula. You plug in your information. Negative 16. This is area, so this would be squared feet per second. Okay. Sometimes you'll have multiple formulas that you'll have to use and you'll have to take the derivatives of. This is an example, good example. We're told that the surface area of a sphere is growing at a rate of 10 cubic meters per second. How fast is the volume of the sphere growing when the radius of the sphere is 5 meters? You will be given, thankfully, the surface area formula, which is 4 pi r squared for a sphere, and the volume formula, which would be 4/3 pi r cubed. But you need to figure out what's going on. We're trying to find how fast is the volume changing. So dV dt equals something. I don't know what it is, but that's what I need to find. Exactly when the radius is 5. We'll plug in 5 after we take our derivatives. We know the surface area, dSA over dt, is 10. So after we've written down this information, we're able to start taking derivatives and using our information to our advantage. We would probably take the derivative of this one first, have 10 plugged in, plug in 5 for the radius to find dr dt. Once we find dr dt, we can take the derivative of this, plug in 5, and plug in the dr dt that we found to find dv dt. Got it? Okay, I'll do that really quick just because. Make sure you put the pi in the denominator if it's going into the denominator. So this is 10 over 40 pi or 1 over 4 pi. Here, I take the derivative of this guy to be dv dt is equal to 4 pi r squared dr dt. dv dt I'm trying to find when r is 5. dr dt I found. And boom, boom, dv dt is just 25. And it's a volume. It would be in cubic. This should be in squared surface area. Okay, so it's just using 2 formula. You use one to get you the other. I will have 2 more examples that I will do on your video that you can watch. Next example, circle's diameter is growing at a rate of 3 centimeters per second. How fast is area growing when its radius is 6 centimeters? Okay, so the diameter we need to understand is twice our radius. So that means that the change in my diameter, I don't know why I'll use another D, maybe a D with that. I feel like I can't even write that anymore. dD dt is equal to 2 dr dt. Okay, so as the diameter is growing at 3 centimeters per second, the radius would be growing at half of that. Okay, how fast is the area growing when the radius is 6 centimeters? Well, we need the area formula, d dt. We get dA dt is equal to 2 pi r dr dt. I plug in dA dt is what I want to find. I have r, and I have dr dt. It's 3 halves, half of d dt. So we'd end up with 18 pi. This is area, so it's be units squared per second. Okay, next one. Volume of the sphere is increasing at 3 pi cubic centimeters per minute. At what rate is its diameter increasing at the instant that the radius of the sphere is 3 centimeters? So volume, dv dt, is 3 pi. We want the diameter, I'll use a capital D, that's probably easier, when the radius is 3. Okay, well, I'm just going to use the volume, 4/3 pi r squared, 4/3 pi r cubed, formula of a sphere, and I'll just have to, just understand that they're asking for the dd dt. Take the derivative, and I get dv dt equals 4 pi r squared dr dt. Okay, so the radius is 3. Again, we'd have to understand the relationship between the diameter and the radius, and that we would have to have our rate at which our diameter is increasing compared to a rate at which our radius is increasing. So I can just solve this for dr dt and plug it in here. In this situation, that might be the best situation. I want to find dd dt. Actually, I can find dr dt, and then I'll be able to find dd dt. Because volume is 3 pi, this is 4 pi, this is going to be 9. This is dr dt, which I'm going to find. I will divide by 36 pi. So 3 pi over 36 pi. The pi's will go away. This will just be 1 over 12. And that's equal to dr dt. So I would multiply that by 2 to get dd dt. 1/6. It is a centimeter. It is a unit to the first power per second. Okay, so relationship there. Here's another one. At some point, the rate that the circumference of a circle is growing is 4 times the rate at which the area is growing. What is the length of the radius at that point? So we need the circumference formula, and we need the area formula. The rate at which the circumference is growing is 4 times the rate at which the area is growing. So the rate at which the circumference is growing, dc dt, is 4 times the rate at which the area is growing. Okay. Well, I can use that to my advantage, and I could take the derivative of probably both, because I'm trying to find the length of the radius. I feel like I might need dr dt, but maybe not. Maybe I have everything I need. This would be 2 pi dr dt. Here I have dA dt is equal to 2 pi r dr dt. So I want to find r. I have this combination that dc dt is equal to 4 dA dt. I can just plug that in to find the r dt. Well, I can solve this for dA dt. There's a lot of different ways to do this. This would be pi over 2 dr dt. I can then take that and plug it in here, and I get pi over 2 dr dt is equal to 2 pi r dr dt. The r dt's will cancel. I'll divide by 2 pi I end up with pi over 4 pi, which is 1 over 4. That is going to be my radius. Okay? So again, using two equations, using our knowledge, taking derivatives with respect to t, using this that we had to generate to help us kind of plug in and substitute to solve. Another thing that's important is that constant values or fixed values can be plugged into formula. Let's take this cylindrical tank. We're losing water at a rate of 5 cubic centimeters per minute. How fast is the height of the water changing? The radius of the tank is 5 feet. Well, the volume of a cylinder is pi r squared h. Okay, and I know that dv dt is equal to -5. I want to find dh dt at the moment when r is 5. Okay, so when the radius is 5. So if the radius of the tank is 5. Now, if we're talking about a cylindrical tank, the radius is always 5. Always and every time 5. So that's not going to change no matter where the water is in the tank. The water's down here or up there. Its radius is always going to be 5. Since that is the case, since this is what we call a fixed value or a constant value, we can go ahead and just plug that into our formula, making a very simplified formula for the volume of the water in this specific tank. And you could take the derivative of this simplified formula to be able to solve your question. This would just be 25 pi dh dt and dv dt is -5. dh dt is what I'm trying to find. I can solve for dh dt by dividing by 25 pi. -1 over 5 pi. This would be in units to the first power, centimeters per minute. Okay, so there's another one. And this is situations where we can simplify things. Always look to simplify. Here's another one just like that. We got 2 more to go. We got the height is growing by 2 inches per second. The length is 4 inches. At what rate is the area of the rectangle changing? So area of a rectangle is base times height, or x times y. Why don't we go with x times y? A horizontal length times a vertical length. Its height, which we'll say is the dy dt. Is growing by 2 inches per second. Its length, we'll say is x is 4 inches. So its length's always 4 inches. At what rate is the area of the rectangle changing? Well, I can just say that this is that, and then if I took the derivative, plug in 2, I get 8. Okay, so this is fixed. Its length is always 4 inches. It's not changing. It's just height is growing. Okay, so I could plug in fixed values to simplify things. Last one, a pile of dirt is growing at a rate of 10 cubic feet per second. That's dv dt. Radius of the pile is always 3 times the size of its radius. Height. The radius of the pile is always 3 times the size of its height, which is how you get 3h is equal to r. Radius is equal to 3 times the size of the height. How quickly is the height of the pile changing? So I want to find dh dt. Probably when their height is given to you, probably when I'm saying h is 2. I probably need that extra piece of information. You'll be given all the pieces of information. The volume of a cone is 1/3 pi r squared h. This is a fixed relationship. That the radius is equal to 3h. I can go ahead and plug in 3h for r to create a simpler formula for the volume of this cone. We just get 3 pi h squared, h cubed. Well, if you take the derivative of this, you will be able to plug in your information and find dH dt. That's important that we want dH dt, we need to have h's in our formula. If we somehow were given the formula or given the situation where like h is equal to 1/3 r, you would not plug in 1/3 r for h and just have r's, because then you wouldn't be able to find dH dt. You need h's. So you would need r equals 3h and plug in 3h so that you have h's. So that's important to note. We'll talk about that more next class, how you got to look for what you need and make sure you have that in your formula. We'd end up with 9 pi h squared dH dt. I'm trying to find dH dt. I have that h is 2, plug it in there. dV dt is 10, plug that in there. Solve for dH dt. And I get 10/36 pi. All right, and that's it. Thank you very much.